A rock from another star system passes the Sun this Wednesday. No fanfare, no apocalypse, just physics and chemistry doing what they do when ice and metal travel 40 trillion miles and brush against our star. You've heard the headlines: alien mothership, Halloween timing, pure nickel without iron. We're cutting through that noise. Here's what actually happens when 3I Atlas reaches perihelion on October 29, 2025. The Atlas telescope, Asteroid Terrestrial Impact Last Alert System, flags a dim object 4.5 astronomical units out just past Jupiter's orbit, moving at 245,000 kilometers per hour. Too fast. The orbit math lands immediately. Eccentricity 6.14. Anything above 1 means you're not coming back. This thing launched from somewhere else and it's passing through. The Minor Planet Center collects 122 observations from 31 observatories within 24 hours. They tag it 3I Atlas on July 2nd. Third interstellar visitor confirmed. A first was 1I Oumuamua in 2017, a tumbling pancake, 440 meters wide, showed up after perihelion already leaving. Second was 2I Borisov in 2019, caught by Gennady Borisov at Margot Observatory in Crimea on August 30th. Borisov looked like a standard comet, water ice, carbon monoxide, behaved normally. 3I Atlas does not. David Jewett and Jane Liu aimed the Nordic Optical Telescope at it on July 2nd, 2025. 2.5 meter aperture perched on La Palma in the Canary Islands, clearly active, a coma 26,400 kilometers across, twice Earth's diameter. That fuzzy cloud shouldn't exist yet. It's still beyond Mars, cold, but something's sublimating. The temperature at that distance measures around negative 170 degrees Celsius. Too cold for water, but perfect for carbon dioxide ice. Test data goes back further. NASA's Transiting Exoplanet Survey satellite caught it on May 7, 2025, at 6.4 astronomical units, already outgassing. That's unusual. Water ice doesn't sublimate that far out. Carbon dioxide does. The TESS observations span May 7th through June 3rd, covering 27 days of continuous monitoring. Brightness measurements show steady activity, no major outbursts, no sudden drops. Just consistent sublimation driven by carbon dioxide ice, transitioning to gas as solar photons hit the surface. Lowell Discovery Telescope in Arizona, 4.3 meter mirror, resolves a marginal tail-like elongation 3 arcseconds long. These early observations establish that 3I Atlas isn't a dead rock, it's shedding material. The International Astronomical Union's Central Bureau for Astronomical Telegrams issues Circular 9983 on July 2nd, confirming cometary activity. Within 72 hours of discovery, astronomers worldwide pivot instruments toward it. Time is limited. Perihelion approaches in 4 months. Every observation matters. Exposure time calibrated to track the comet's motion against background stars. Stars streak, comet stays sharp. Image shows a teardrop cocoon, dust streaming off the nucleus. No classic tail yet. The grains are big, 0.1 millimeter radius, and slow, 5 meters per second. Ejection speed. Takes time for radiation pressure to push them. Small particles, micron-sized, are missing or buried. Dust production rate estimated at 6 kilograms per second for small particles, 180 kilograms per second total at 2 astronomical units. By August's end, Gemini South measures the tail at 30 arcseconds, 56,000 kilometers long. The 8.2 meter mirror at Gemini South Telescope on Cerro Pachon in Chile uses the GMOS instrument, Gemini Multi-Object Spectrograph, for deep multicolor imaging during a shadow, the scientists' public outreach session on August 27th. Karen Meach from University of Hawaii leads the observation. The public watches live via Zoom as the telescope tracks the comet across Libra. The tail shows up clearly now, extending about 1/12 of a degree. A full moon measures half a degree for comparison. James Webb Space Telescope turns its near-infrared spectrograph on August 6th. NIRSpec operates in the 1 to 5 micron wavelength range, perfect for detecting molecular ices and gases. Results drop August 25th via NASA press release and European Space Agency announcement. Carbon dioxide dominates. CO2 to H2O ratio roughly 8 to 1. Standard comets run the opposite, 80% water, not 4%. This comet is dry. Carbon dioxide with traces of water, carbon monoxide, carbonyl sulfide. The spectral lines are sharp, indicating cold gas expanding from the nucleus. No high temperature minerals detected, no silicates, no pyroxenes, just volatiles. The carbon dioxide emission is bright enough to measure production rates, approximately 300 kilograms per second at 3 astronomical units. That's enough to lift the dust we see. Water production much weaker, maybe 40 kilograms per second. The mass ratio matches the spectral ratio. This thing formed where carbon dioxide froze preferentially over water, or cosmic ray processing converted surface water to carbon dioxide over billions of years in interstellar space. NASA's Sphere-X mission, spectrophotometer for the history of the universe, epoch of ionization and ICES explorer, observes it mid-August. Sphere-X specializes in near-infrared spectroscopy across the entire sky. Data released August 21st confirms carbon dioxide gas and water ice signatures in the infrared. The ice signature means solid particles of water ice in the coma, not just vapor. Small ice grains mixed with the dust, reflecting sunlight in characteristic wavelengths. Sphere-X also detects organic molecules, carbonaceous compounds formed from carbon monoxide and carbon dioxide reactions, consistent with Tholen's processing. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Minor Planet Center's official confirmation, published July 2nd, 2025, NASA's public data releases from Hubble, observations archived July 21st, JWST and IR spec findings announced August 25th, and peer-reviewed preprint papers from David Jewett's team submitted to Archive on October 21st, 2025, analyzing Nordic optical telescope data from July through September. These aren't press releases, these are observation logs with instrument specifications and photometric measurements. Now back to the information. Visible only through Sirius telescopes, 3 to 4.5 inch apertures with image stacking. Citizen scientists using Unistellar network telescopes track it. Vamshi Kesireddy in the United States captures images. The network consists of smart telescopes operated worldwide, compensating for the comet's rapid motion through automated tracking algorithms. It's setting 2.5 hours after the sun. Equatorial observers get the best shot. Northern and southern latitudes see it scraping the horizon. The Very Large Telescope in Chile, UVES spectrograph, ultraviolet and visual Echelle spectrograph, catches something strange. 4 8.2-meter telescopes working as individual units or combined interferometrically. UVES sits on Unit Telescope 2, named Quayan. High-resolution spectroscopy, wavelength range 300 to 1100 nanometers. Nickel emission lines at 352.45 nanometers. Strong. Iron emission lines at 372 nanometers. Absent at first, then weak. Reported by Damien Hutzemakers and team in a preprint dated September 28th, posted to Arch4 October 1st. 6 time bins, heliocentric distances 3.14 to 2.14 astronomical units. Observation span July 23rd through September 19th. Nickel shows up every time. Iron only appears closer than 2.64 AU. The nickel to iron ratio starts at 100 to 1, drops to 10 to 1 as the comet warms. Orders of magnitude higher than any known comet, including 2 I Borisov. They form together in supernovae, lock into silicate and sulfide grains. Chondritic meteorites, primitive samples of solar system material, show nickel-iron ratios close to 1 to 20 by mass, matching solar abundances. The temperature where comets operate, -100 to -50 Celsius at these distances, way below what's needed to vaporize those minerals. Silicate sublimation requires 1500 Kelvin. We're at 150 Kelvin. So how's nickel getting into the coma? Not from thermal sublimation of rock. Has to be a volatile carrier. Thomas Puzia at Pontificia Universidad Católica de Chile analyzes the VLT data with his PhD students. They notice the nickel lines appear asymmetric, blue-shifted by up to 2 kilometers per second, indicating gas flowing toward Earth faster than the comet's bulk motion, anisotropic outgassing from active vents on the day side. Gran Telescopio Canarias on La Palma, 10.4-meter primary mirror, largest single-aperture optical telescope in the world, images the coma at high resolution in August. Diameter measurements show the coma is slightly elliptical, 26,400 by 24,700 kilometers. Elongation suggests rotation or directional outgassing. No clear jets resolved yet, but asymmetry is there. The coma's brightness follows an inverse square law with distance from the nucleus out to about 10,000 kilometers, then flattens. That transition marks where freshly ejected gas and dust reach equilibrium with solar radiation and expand ballistically. Inside that radius, collisions matter. Outside, it's free expansion. Explains the nickel-only signature early on. As the comet heats up closer to the sun, iron pentacarbonyl joins the party. The ratio drops. Simple chemistry. Strange location for it, but chemistry doesn't care about expectations. Nickel and cyanide emissions, extending hundreds of kilometers from the nucleus. Hydrogen cyanide production rate measured by James Clerk Maxwell Telescope on September 7th. 1.5 times 10 to the 25 molecules per second at 2.33 AU. 1 week later, September 14th, it triples to 4.5 times 10 to the 25 molecules per second. 2 kilograms per second of HCN. The comet's waking up. Nordic Optical Telescope tracks brightness through September. Power law with exponent 3.8 plus or minus 0.3. Dust production scales as heliocentric distance to the negative 1.8, consistent with carbon dioxide driving activity. Nothing exotic in the light curve. Volatile material heating up, standard physics. October 3rd, 2025. Closest approach to Mars, 29 million kilometers. ESA's ExoMars, Trace, Gas Orbiter, and Mars Express pivot. TGO's Cassis camera grabs frames, exposure time 5 seconds. The comet appears as a slightly fuzzy white dot against streaked stars. The camera's built for Mars' surface, bright, close. 3i Atlas is faint, far. They get images anyway. Mars Express tries 0.5-second exposures, too short. Object doesn't show. Scientists stack images later, might pull signal from noise. The coma is there, a few thousand kilometers wide, but too dim to measure edges. No resolved nucleus. That would be like spotting a cell phone on the moon from Earth. The spectrometers, Nomad on TGO, Omega, and SpyCam on Mars Express, swing toward it. Jury's out on whether they got usable spectra. Data analysis runs for months. GOES 19. Weather satellite, equipped with a coronagraph, catches glimpses October 18th through 24th. Magnitude 12 detection. Citizen scientist Warchate Boonplod spots it in CCOR-1 images. Otherwise, Earth-based optical astronomy goes dark. The comet is occulted until November. Mercury gets 10 times nearer every 88 days. Doesn't make news. But 3i Atlas isn't from here. It's crossing the sun's energy gradient at 68 kilometers per second with respect to the sun. Velocity measured via Doppler shift of emission lines. Red shifted on the receding limb of the coma, blue shifted on the approaching side. Solar radiation at perihelion delivers 33 gigawatts of power to the surface. Equivalent to 33 nuclear reactors at full output, all focused on a nucleus between 5 and 6 kilometers wide. The solar constant at Earth orbit measures 1,361 watts per square meter. At 1.356 AU, it drops to about 740 watts per square meter. A 5-kilometer sphere has a cross-section of about 20 square kilometers. 20 million square meters times 740 watts equals 15 gigawatts if the albedo is 0. If the nucleus reflects 40%, typical for comet nuclei, absorbed flux is 9 gigawatts. But the estimates account for subsolar heating and local temperature spikes. 33 gigawatts total energy processing across the entire surface over the perihelion window. The minimum diameter, derived from brightness and lack of non-gravitational acceleration through September, is 5 kilometers. Upper limit from Hubble as of August 20th, 5.6 kilometers. Could be as small as 440 meters, but trajectory constraints and mass estimates push it bigger. Avi Loeb and Richard Cloete calculate minimum mass from trajectory stability. If the comet showed non-gravitational acceleration like outgassing thrust, orbital parameters would shift detectably. They don't. That means either the comet isn't outgassing, wrong, we see the coma, or it's massive enough that outgassing forces are negligible. The calculation requires at least 33 billion tons, 33 trillion kilograms, million times 1 I Oumuamua's mass, 1,000 times 2 I Borisov's. For comparison, 2 I Borisov measured about 450 meters wide, with a mass near 1 trillion kilograms. 1 I Oumuamua was smaller still, roughly 100 meters by 400 meters pancake, maybe 40 billion kilograms. 3I Atlas dominates both. It's in a different category. If you're still watching and you want more deep research like this, hitting you with exact measurements, dates, instrument names, preprint citations from researchers like Loeb and Jewett, subscribe now. This is what real documentation looks like. Not headlines, not hype. Just instrument data from the Nordic Optical Telescope published in Ore Archaeus preprint 251 0.18769, submitted October 21st, 2025, and Very Large Telescope UVES spectra from Hutzenmakers cited in Archifer preprint analyzing metal emissions. Comment below from which city you're hearing this. Now back to the perihelion mechanics. The subsolar point, where sun hits perpendicular, reaches maybe 200 Kelvin. Still cold by Earth standards, but hot enough for carbon dioxide ice to sublimate aggressively. Sublimation absorbs energy, latent heat, so the surface doesn't heat uniformly. Active regions where ice transitions to gas stay cooler than bare rock. Thermal models of comet nuclei show temperature gradients. Sunlit ice at 180 Kelvin, shadowed craters at 100 Kelvin, bare silicate patches at 220 Kelvin. 3. I-Atlas probably has mixed terrain. Ice-rich zones driving gas production, dust-mantled zones reflecting heat. Sublimation accelerates. Dust embedded in the ice gets released, ejected at those 5 meters per second by gas drag. The coma expands. Production rates climb. Hydrogen cyanide jumps from 4.5 times 10 to the 25 molecules per second in mid-September to potentially 10 times that at perihelion. Nickel emission intensifies as more tetracarbonyl breaks down under increased ultraviolet flux. If there's deeper water ice under a CO2 crust, cooked by cosmic rays during billions of years in interstellar space, heat might crack that crust, expose water, change the volatile mix. 2, Borisov did that. Pre-perihelion, it showed carbon monoxide and water. Post-perihelion, the water dried up. Ratio flipped. Carbon monoxide stayed strong, suggested layering. Water ice on top got depleted. Carbon monoxide ice underneath kept sublimating. Might happen here or might not. Depends on layering. Depends on whether the nucleus is solid monolithic ice or rubble pile. Depends on spin. We don't know rotation period yet. No resolved light curve. Observations through September showed steady brightness, no periodic variations. If the comet rotates slowly, once per week, variations are shallow. If it's tumbling chaotically like Oumuamua, light curve gets complicated. If it rotates fast, once per day, we'd see fluctuations. We don't, so either slow or symmetric. More data needed. Normal comet tails aim away from the sun, radiation pressure. This one points inward. Explained 2 ways. Geometry. If the dust sheet is edge on to Earth, projection effects fake a sunward jet. Or real anisotropic outgassing, vents on the day side pushing material toward the sun before radiation pressure takes over. Nordic Optical Telescope images from July show a sun-facing dust fan. By late August, it's flipped to anti-solar tail. Dust grains are heavy, slow to respond. Not a mystery. Just delayed dynamics. Adam Hibbard, colleague of Avi Loeb, floated the idea. If it's artificial and the anti-tail is breaking thrust, the flip near perihelion makes sense. Fun idea. Zero supporting evidence. Occam's razor leans comet. Polarization measurements from Very Large Telescope, Nordic Optical Telescope, Rosen Observatory through July and August reveal extreme negative polarization. Light reflected off the coma oscillates along the Sun-Comet observer plane, a higher degree than typical comets. Similar to trans-Neptunian objects, suggests a mix of icy and dark organic material, tholins, complex molecules formed when ultraviolet light or cosmic rays hit simple carbon compounds. Kuiper belt objects show it. Interstellar space bombards anything drifting through with radiation for billions of years. Surface gets processed. Reddish color. Organic crust. 3I Atlas has that signature. Avi Loeb, Harvard astrophysicist. Frank B. Baird, junior professor of science, director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, ranks at 4 on the Loeb scale he developed with Omer Eldadi and Gershon Tenenbaum in a paper published September 2025. Scale runs 0 to 10. 0 is natural, fully explained by conventional astrophysics. 10 is confirmed artificial threat on collision course with Earth. 4 is unusual but not conclusive. Anomalies present that challenge natural explanations, but insufficient evidence for artificiality. He lists 8 anomalies documented through peer-reviewed observations and statistical analysis. 1. Trajectory aligns within 5 degrees of the ecliptic plane. The ecliptic is the disk containing Earth, Mars, Venus, Jupiter. Planetary orbits. Objects arriving from random interstellar directions should have inclinations distributed uniformly across 90 degrees. 5-degree alignment probability, about 0.2%. Statistically, interstellar objects should arrive isotropically, unless their ejection mechanisms favor disk alignments, which current planet formation models don't predict strongly. Most comets show tails pushed away from the sun by radiation pressure and solar wind. 3 I-Atlas shows material pointing sunward in July images. Geometric projection can fake this if the dust sheet lies edge-on to Earth. But spectroscopic measurements indicate real motion toward the sun at a few kilometers per second in certain coma regions. Anisotropic jetting from active vents on the sun-facing hemisphere could explain it. Not conclusive for artificiality, natural comets have jets, but the geometry is atypical. 3. Mass million times larger than Oumuamua, 1,000 times larger than Borisov. If interstellar objects follow a size distribution similar to asteroids, power law with more small objects than large, we should discover many small interstellar visitors before spotting a big one. The detection rate expectation based on Oumuamua's size. Roughly 1 Oumuamua per year, 1 Borisov per decade, 1 3I Atlas per century or millennium. We got 3I Atlas 8 years after Oumuamua. Either we're lucky, or the size distribution is different, or detection biases favor big, bright objects. Loeb argues the statistics are off. Critics argue small sample size, 3 objects, makes statistical inference premature. 4. Arrival timing allows planetary flybys, Mars on October 3rd at 29 million kilometers, Venus on November 3rd at 97 million kilometers, Jupiter on March 16th, 2026 at 54 million kilometers, while being unobservable from Earth at perihelion due to solar conjunction. The combination has 0.005% likelihood for a random hyperbolic trajectory. It's passing the Sun when Earth can't watch, then visiting the major planets on its way out. Could be coincidence, could be planned. No way to distinguish without more interstellar objects for comparison. Nickel to cyanide ratio similarly extreme. HCN production measured in grams per second, nickel production also grams per second. Comets usually have trace metal emissions, swamped by molecular lines. 3, I-Atlas has bright metal lines. The carbonyl hypothesis explains it naturally. Nickel tetracarbonyl sublimates easily, releases nickel. Iron pentacarbonyl joins later. Chemistry works. But where did the carbonyls form? Protoplanetary disks around certain stars? Interstellar processing? Unknown. 6. Water content 4% versus typical 80%. JWST and SphereX data confirm. Carbon dioxide dominates by mass. Water is minor. Solar system comets, even those from the Oort cloud, formed in the outer solar system, stored in deep freeze for billions of years, contain majority water ice. Exceptions exist. Some Jupiter family comets are carbon monoxide or carbon dioxide rich, but 4% water is low. Suggests formation in an environment where water didn't condense preferentially, or cosmic ray radiolysis converted water to carbon dioxide over eons. Negative polarization means perpendicular oscillation dominates parallel oscillation at small phase angles, backward scattering geometry, seen in trans-Neptunian objects with complex organic surfaces. 3 I-Atlas shows it strongly, implies tholins or similar organics coating the dust. Not artificial, but unusual for an active comet. Most active comets have positive polarization from fresh ice and small dust grains. Big Ear Radio Telescope at Ohio State University. 72 seconds of narrowband emission at 1,420 megahertz, 61 times background noise. Never repeated. Coordinates in Sagittarius, right ascension 19 hours 25 minutes, declination minus 27 degrees. 3 I-Atlas trajectory extrapolates back to Sagittarius within 9 degrees. Angular separation 9 degrees covers about 0.6% of the sky. Coincidence probability, 0.6% if purely random. Loeb notes it. Most astronomers call it cherry picking. Choose any historical signal, you'll find something within a few degrees eventually. No causality, no connection, just human seeing patterns. Stack those 8 anomalies, multiply the probabilities. Assuming independence, not valid statistically, but illustrative, you get 0.2% times 0.5% times 0.005% times 0.6% times the rarity of the chemical and polarization anomalies. Product lands around 1 in 10 quadrillion if you push the math. Loeb's argument, something this improbable warrants not dismissing the artificial hypothesis outright. The cumulative weirdness exceeds random chance. Most of the astronomical community disagrees. The anomalies have natural explanations. Ecliptic alignment could be selection bias. We spot objects near the ecliptic more easily. Surveys focus there. Mass difference is sampling. Small objects are common, big ones rare. Statistics say we'll see a range. 3 objects isn't a population. Planetary flyby timing is cherry picking. Lots of objects pass planets. We notice the close ones. Chemical anomalies fit exotic comet compositions from different stellar environments. Carbon-rich protoplanetary disks produce carbon dioxide ices. Polarization fits tholins. Cosmic ray processing over billions of years changes surface properties. Wow, signal alignment is coincidence? 9 degrees is a big cone in sky coordinates, billions of stars, trillions of comets over galactic history. Overlaps happen. Loeb counters, science advances by not ignoring anomalies. Oumuamua's non-gravitational acceleration was dismissed initially, then confirmed. Fair point. Data decides. He's running the Galileo project to search for technological signatures on interstellar objects and unidentified aerial phenomena. Controversial, but methodologically rigorous. Testable hypotheses, falsifiable predictions. If 3 I-Atlas were artificial and executed a maneuver while behind the Sun, unobservable, it could change trajectory. Maybe slow down, maybe redirect toward inner planets. Loeb calls it a black swan event. Low probability, huge implications. He says we must watch post-perihelion for trajectory deviations. If it emerges from solar conjunction and the orbit has shifted beyond what solar radiation pressure and outgassing can account for, that's a signal. Natural comets don't maneuver. Outgassing creates non-gravitational acceleration. 2I Borisov had it, subtle, matched models. 1I Oumuamua had it too, controversial. Debated whether it was outgassing or something else. 3I Atlas shows no detectable non-gravitational acceleration through September. Trajectory matches pure gravity. If that changes post-perihelion, eyebrows raise. Spacecraft is en route to Jupiter, launched April 14, 2023, from Kourou, French Guiana, aboard Ariane 5 rocket. Won't arrive at Jupiter until July 2031, but it's in position to observe 3I Atlas post-perihelion. Instruments: Janus Visible Imager, Jovis Amorum Acnitorum, Undique Scrutator, scrutinizer of Jupiter's loves and children everywhere, 13 filter camera system covering 340 to 1080 nanometers. Magus Infrared Spectrometer, Moons in Jupiter. Imaging Spectrometer, covers 500 to 5,500 nanometers, maps surface composition through spectral fingerprints. SWI Submillimeter Wave Instrument. Submillimeter Wave Instrument operates at 500 to 600 gigahertz, detects water, ammonia, other volatiles, and gas phase. Can detect coma gas composition, surface properties if the nucleus is resolved, thermal emissions indicating subsurface temperature. Data expected mid-November. JUICE also carries GALA, Ganymede, laser altimeter, but won't be useful for 3I Atlas flyby due to distance. The spacecraft's trajectory takes it on a Venus flyby August 2025, Earth flybys August 2024 and September 2026, then final Earth gravity assist January 2031 before Jupiter insertion. The 3I Atlas encounter is opportunistic. JUICE isn't designed for comets, but instruments are sensitive enough to capture data. Still not close, but ground-based telescopes get clear shots. Keck Observatory in Hawaii, twin 10-meter mirrors on Mauna Kea, can use Heyer's spectrograph for high-resolution spectroscopy, measuring Doppler shifts to 1 meter per second precision. Very Large Telescope in Chile brings all four 8.2-meter units to bear, combining light interferometrically with VLTI. Very Large Telescope interferometer, achieving angular resolution equivalent to a 130-meter mirror, can resolve coma structure down to milliarc second scales. Gemini North and South, 8-meter mirrors in Hawaii and Chile, provide multi-wavelength imaging and spectroscopy. Nordic Optical Telescope continues photometry tracking brightness evolution. Vera Rubin Observatory, now fully operational in Chile, 8.4-meter primary mirror, 3.5 billion pixel camera, widest field of view in astronomy, will image 3I Atlas every few nights as part of its legacy survey of space and time. Data products include light curves, color measurements, astrometry accurate to tens of milliarc seconds, high-resolution spectra, multi-wavelength imaging. The comet will be fading, moving away from Sun, dropping below magnitude 13, but activity lingers. Carbon dioxide sublimation continues out to 3 AU. Hydrogen cyanide production detectable even farther. This is when we compare pre-perihelion chemistry to post-perihelion. Did water ice emerge from under the CO2 crust? Did the nickel-iron ratio normalize as predicted? Did the coma composition shift toward more typical comet ratios? Did outbursts occur indicating fresh ice exposure? Did fragmentation happen? Answers matter. If volatile mix changes, confirms layering models, carbon dioxide mantle over water ice core. If it stays weird, confirms the weirdness is intrinsic to the object's formation environment. If brightness spikes, suggests fragmentation or outburst. If it fades smoothly, suggests stable nucleus. 0.36 AU. NASA's Juno spacecraft, in Jupiter orbit since July 5, 2016, can observe. Juno's orbit is highly elliptical. Perigove passes within 4,000 kilometers of Jupiter's cloud tops every 53 days. Apogee stretches out to 8 million kilometers. During March 2026, orbital geometry places Juno in position to view 3I Atlas. Instruments: UVS, ultraviolet spectrograph, operates at 68 to 210 nanometers, detects atomic hydrogen, sulfur, oxygen emissions, and cometary comas. JRAM, Jovian Infrared Auroral Mapper, covers 2 to 5 microns, measures thermal emission, and maps surface temperatures. MWR, microwave radiometer, operates at 6 frequencies from 600 MHz to 22 GHz, detects thermal emission from subsurface layers up to 100 kilometers deep in atmospheres. For a comet, MWR could constrain nucleus porosity and thermal properties. Juno also carries WAVES instrument detecting radio emissions from 10 kHz to 41 MHz, and JunoCam Visible Imager for public outreach. Measures, outgassing patterns, thermal emission, potentially radio signatures. Loeb pushed for this in multiple op-eds and submitted formal observation requests to NASA in October. He wants Juno to search for artificial radio signals. Natural comets don't broadcast coherent radio. Plasma interactions with solar wind produce noise, but not narrowband carriers. If 3I Atlas emits structured radio, modulated signal repeating pattern, game over its technology. No signals expected. Lightning doesn't happen in comet comas. No charge separation mechanism, but checking costs nothing except telescope time and data storage. NASA approved the observation window. Results expected late March 2026. Tracked vertical excursion from the galactic midplane. Stars scatter over time, thicken the disk. Young stars hug the midplane, old stars wander. 3I Atlas climbs high, about 0.02 kiloparsecs maximum excursion, consistent with thick disk population. Median age, 4.6 billion years. Older than 1I Oumuamua, 1 billion years. Older than 2I Borisov, 1.7 billion years. 3I Atlas formed when the Milky Way was younger, metal-poor stars, different chemistry. It's been drifting for most of the galaxy's history. Took 800 million years to migrate from the opposite side of the disk to here, cosmic wanderer. Jupiter alone ejects roughly 1 comet per century to interstellar space based on dynamical simulations. Multiply by 200 billion stars in the galaxy, assume half have Jupiter-mass planets, run for 10 billion years, you get 10 to the 20th power interstellar comets, drifting through the Milky Way. Only a tiny fraction pass through any given cubic parsec per year, but the numbers add up. 1I Oumuamua came from the thin disk, likely a young planetary system still clearing debris. Ejection velocities match what you'd expect from giant planet scattering, 10 to 30 kilometers per second relative to the parent star. 2I Borisov, intermediate age, maybe a mature system with established planets kicking leftovers out. 3I Atlas, thick disk, old system, low metallicity. Carbon dioxide rich because it formed far from its star, cold zone where CO2 freezes. Outer regions of protoplanetary disks beyond the snowline, 5 AU in the solar system, accumulate water ice. Beyond 10 AU, carbon monoxide freezes. Beyond 20 AU, where temperatures drop below 50 Kelvin, carbon dioxide freezes too. 3I Atlas probably formed beyond 20 AU in its home system, accreted carbon dioxide preferentially. Water is less abundant in low metallicity environments, fewer oxygen atoms per hydrogen atom compared to solar composition. Early universe chemistry produced hydrogen and helium. Metals, everything heavier, came from supernovae. Older stellar populations have lower metallicity. Explains the dry comet. The thick disk formed 4 to 10 billion years ago during the Milky Way's early chaotic phase. Stars from that era have 1/10 to 1/4 solar metallicity. Planet formation still happens, but with different abundances. Carbon dioxide over water makes sense. Nice model, named after Nice, France, where it was developed, describes how Jupiter, Saturn, Uranus, Neptune migrated outward in the early solar system, scattering planetesimals into the Oort cloud or interstellar space. Similar process in 3I Atlas's home system billions of years ago. A 5-kilometer comet encountering a Jupiter-mass planet at 10 AU gets accelerated to escape velocity, 20 to 50 kilometers per second. Add the parent star's motion around the galactic center, 230 kilometers per second, and you get hyperbolic galactic orbit. 3. I-Atlas has been wandering for 4.6 billion years, covering roughly 4,000 light years in that time. It passed through molecular clouds, stellar nurseries, supernova remnants. Cosmic rays pummeled the surface. Solar wind from nearby stars stripped surface layers. Interstellar dust impacts eroded the nucleus. By the time it entered our solar system in 2025, it carried the chemical and physical history of half the galaxy's lifetime. June 21st to July 3rd, 2025, during science validation. Coma diameter grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. Rate of growth, 570 kilometers per day. Consistent with sublimation, ramping up as heliocentric distance decreased from 4.7 to 4.5 AU. Serendipitous catch. If Rubin had started science validation 2 weeks earlier, it would have discovered 3I Atlas before Atlas did. Rubin goes fully operational in 2026. First flight occurred May 15, 2025, with commissioning observations through December. Full survey starts January 2026. Expectations: 2 orders of magnitude increase in interstellar object detection rate. Atlas found one in 8 years since it began operations. Rubin should find 10 to 100 per decade. Survey covers the entire southern sky every 3 nights to magnitude 24.5. 3I Atlas at magnitude 17 in July was trivial. We might find 4I within a year or two of Rubin operations, 5I and 6I by 2030. Population statistics improve. We'll learn if 3I Atlas is unusual among interstellar visitors or typical. Right now, sample size 3. 1 pancake, Oumuamua, no coma, tumbling weird acceleration. 1 normal comet, Borisov, water and carbon monoxide, standard dust-to-gas ratio, fragmentation event. 1 dry, nickel-rich giant, 3I Atlas. Not enough to generalize. Need dozens. Rubin delivers. When we have 50 interstellar objects cataloged, we'll see distributions. Size, composition, activity level, trajectory. We'll constrain planet formation models across different stellar types and ages. We'll measure ejection velocities and infer planetary architectures in other systems. Interstellar objects are free samples from exoplanetary systems. Better than transits and radial velocity, we get direct material. NEO Surveyor, launching 2027, will catch more. Machine learning pipelines filter candidates. The process: detect moving object, measure astrometry across multiple nights, compute orbit, check eccentricity. Anything above 1.0 gets flagged. Spectroscopy confirms composition. Rapid response networks activate. Hubble, JWST, ground-based telescopes. Time matters. Oumuamua was discovered outbound, only observed for 2 months. Borisov had a year. 3I Atlas gets 9 months inbound, a year outbound. Future discoveries might get years if we catch them early. Composition mysteries remain. Nickel without iron, solved if nickel tetracarbonyl sublimes first. But where did the nickel tetracarbonyl come from? Industrial processes make it. Nature can too. Carbon monoxide reacts with nickel metal under the right conditions. Requires metallic nickel grains in a carbon-rich environment. Possible in protoplanetary disks around carbon stars or in certain nebular regions. Not common, but not impossible. The coma's nickel production rate measured 5 grams per second at 2.8 AU. Iron shows up closer in. Ratio drops. By perihelion, it might look like a normal comet. That's what Hutzemecher's team predicted in their preprint. Comet will become indistinguishable from solar system comets with respect to nickel-iron ratio as it heats further. Several micrometers radius, organic coating. Small grains, 1 micron, eject fast, 22 meters per second. Large grains, 100 microns, eject slow, 2 meters per second. Radiation pressure affects small grains more, they form the tail. Big grains, hang close, form the coma. 3I Atlas has more big grains. Either it formed with them or interparticle cohesion glues small grains together. Borisov had similar large grain dominance. Happens when internal stresses from heating exceed tensile strength. Rubble pile comets crack under thermal expansion. 3I Atlas might fragment at perihelion or might not. Depends on nucleus integrity. We'll know in November when it reemerges. If brightness suddenly spikes, outburst from fresh ice exposure. If it dims and spreads, fragmentation. If it's steady, solid core. Social media ran wild. Actual science got buried. So let's ground it. 3I Atlas is a comet. Interstellar, yes. Unusual chemistry, yes. Big, yes. Artificially constructed, no evidence. The Loeb scale rank 4 means unusual pending more data, not probably artificial. Loeb himself says rank could drop to 2 or 0 with better observations. Baseline expectation is natural object with exotic properties. If JUICE and Juno get clear observations, we'll constrain nucleus size, measure rotation, map surface composition, detect any non-gravitational forces. If ground-based telescopes track it through December and into 2026, we'll see how volatile production evolves, whether water content increases, whether chemistry normalizes. All of that feeds into understanding interstellar object diversity, planet formation, across different stellar environments, and how much chemistry varies star to star. No telescopes watching, just solar flux doing its work, sublimation ramping up, nickel atoms filling the coma, carbon dioxide gas expanding, dust grains accelerating outward. Standard comet behavior scaled up and moved to interstellar chemistry. When it emerges in November, we'll see what changed. One final data point. The orbit integration shows 3I Atlas came from galactic coordinates in Sagittarius, direction of the WOW signal. That signal, 1,420 megahertz, 72 seconds, 6 EQUJ5 on the printout, August 15, 1977. Jerry Amon circled it, wrote WOW in the margin, never repeated despite follow-ups. Theories: terrestrial interference, brief pulsar, deep space masser, alien broadcast, no consensus. The comet's trajectory traces back through space for hundreds of millions of years. By the time the WOW signal transmitted, if it transmitted, 3I Atlas was already millions of miles from that region. No connection. Pure geometric coincidence. 9-degree alignment in a sphere is 2/100ths of the sky. Given billions of stars, thousands of comets, decades of signals, overlaps happen. Loeb argues it's worth noting. Everyone else says it's noise. Data will decide. If Juno or JUICE detect a radio signal from 3I Atlas, the WOW alignment becomes interesting retroactively. If they detect silence, it stays a footnote. No revelation, just another chunk of ice and rock from a system that died before ours formed, taking a shortcut through our neighborhood on its way back to the void. We measure it, we learn from it, we move on. That's the science. That's the story. That's Wednesday without the hype.